1, 2, 3, 4, 5, 6, 7, 8, 1. Alright, I don't even know what to say. Let me start with this. I am here at MIT and I've made friends with scientists. And I meet people and they're talking about all these things and I don't even, like, half of the time I have no idea what they're talking about. Yeah, everywhere you go you just meet some person doing some crazy shit. Like the other day I had to get my bike, like my bike chain replaced, and there's a really sweet thing that they do here. It's called the Bike Lab, but it's just like a group of volunteers who help fix bikes. So I went into the thing, and then this guy was helping me, and then, you know, I'm just like chit-chatting, asking him, you know, about himself, and then asked him what he was studying, and he's like, oh, you know, I'm just like finding some dark matter. It's like, how do you say that with such a casual face? Yeah, like every single conversation here is like, what are you, do you even know what you're talking about, or how crazy that sounds? Anyway, I picked up a bag the other day and I realized that I didn't have a grinder. So I went to one of MIT's shops to 3D print it. And as I was printing it, like the printer didn't work. And there was a guy standing next to me, so I asked him if he could help me out. And yeah, he was really sweet, you know, and helped me out, put the plastic in, and started printing. And as we were talking, yeah, I asked him about himself, and, you know, where are you from, this and that. His name is Stefano. And yeah, I asked him what he was doing research on, and he said it was quantum dots. So I was like, what? And he pulls out his keychain, and he said that he shows me this keychain, and in there are quantum dots. So yeah, I've asked him to come join me in this first video. I legit spoke to this guy for like 10 minutes and I was like, yeah, like, do you want to be in my video? Because I've been having this idea for a while now. I just never really had time to do it. And so now here we are. Okay, alright, we sound check again. 1, 2, 3.
Sound checking again. Do you hear me well?
Alright, so we're good. Well, Stefano, tell me more. Tell where you from, who you are.
I'm from Italy. I came here at MIT recently, like 2 weeks ago.
Yeah.
From Sweden, actually. So I took a long detour from my home city, that is Genoa in Liguria, like northwest of Italy on the coastline. A really nice place. And I'm a chemist, accidentally in chemical engineering now, but I'm actually a chemist, not an engineer. And I tried my best to do some research on nanomaterials.
You came here 2 weeks ago. I met you 2 days ago. So we were 3D printing things, and then you told me about quantum dots.
Yep, I did.
What are quantum dots?
Okay, so that's gonna be fun to explain. So there is an easy way, sort of, to explain what quantum dots are, but we need to move step by step, like little build-ups. So the first thing you need to know is that quantum dots are crystals.
Right.
So we need to explain first what crystals are. Basically, a crystal is just a chunk of matter that is made of ordered atoms. So you take a lot of atoms, all equal to each other, you stack them all together in a very ordered fashion. That is what a crystal is, right? And we have experience of crystals in everyday life, in like a lot of situations. A kitchen salt is a crystal. Sugar is a crystal.
Right.
But also, you know, the silicon inside your smartphone grows in crystals.
Yeah.
The metal in your like gold ring, if you have one, is a crystal. Rocks are made of crystals. So it's like a common form of solid matter, right? So in essence, quantum dots are very small crystals. That's what they are. Of course, they are not your regular crystals. Like, you cannot, you know, take sugar, make it really small, and it will become quantum dot. it must be some special material.
Right.
And the material that you use to make them must be a semiconductor. Again, semiconductor, another small step in our story, right? What is a semiconductor? I'm sure you're familiar with the term because everyone speaks about semiconductors, like they're important for electronics, right? These kind of things.
I'm familiar with the term, but it's like one of those things where you hear it a lot and you think you know it, but you never actually know what it is.
And so now we're going to explain what a
Right.
semiconductor is. All right.
Yeah.
So the secret is in the name, right? Semiconductor means something that conduces electricity, but not too well.
Okay.
That's what it is, right?
Oh, right.
If you take a metal,
Yeah.
that is a conductor. You can attach a battery from one side to the other, and current will flow freely.
Yeah.
If you take something like glass or a piece of ceramic, that is an insulator, so that will not conduce electricity. If you plug a battery from two sides, nothing will happen.
Right.
A semiconductor is something in between. It's like either a very poor conductor or a very bad insulator. You have to decide. Like so,
Right.
when you attach the electricity from two sides, like you apply a bias, some electricity, if your power is strong enough, will start flowing. So that's what a semiconductor is. And for a chemist, a semiconductor is a set of materials. Some are famous, like silicon is semiconductor, indium phosphide, you name it. There are many, right? So, but the point is, all these materials, what they have in common is that they are these bad conductors, bad insulators, something in between. And this is what makes them useful, right? Because the fact that they can or cannot, depending on the conditions, have current flow is what makes, for example, a computer work.
Okay.
That's pretty much it.
Wait, to backtrack a bit, like
Yes.
quantum dots are crystals.
Quantum dots are very small crystals of semiconductor materials.
Okay.
Like imagine, because a crystal is made of something, right?
Yeah,
so
yeah.
your again, kitchen salt is a crystal of sodium chloride.
Right.
A rock
Yeah.
is composed of crystals of usually something like silicates or stuff like that. The chips in your smartphone
Yeah.
are crystals made of silicon.
Okay.
A quantum
okay.
dot
I see.
is a small crystal made of a semiconductor. Okay, so the interesting thing is that so basically we said these quantum dots are small crystals of these semiconductors, and when you make them small, some magic stuff happens. That's why they're interesting.
So it's the same compound. It's just in much smaller size.
Correct.
Okay.
It's
okay.
just in much smaller size, and I mean to understand how small, it's scary actually how small they are. So the scale of our lives is meters, right? We are used to think and work in meters. Like these things are 10 to the power of -9 meters, which is a very scientific and not intuitive way to say the size. If you compare them to something that you consider really small, probably that's not nearly small enough. A blood cell is already several thousand times bigger than them.
That's crazy.
Something that we got unfortunately acquainted to during the last, let's say, 5 years, like COVID virus,
Yeah.
it's still 100 times bigger, around 100 times bigger. I found a nice example that's like super common in the environment of material scientists to explain. So if you take like football ball,
Yeah.
and you compare its size to the entire planet Earth,
Right, yeah.
the difference in size is the same that is between one quantum dot and the soccer ball. So that's the same proportion. Like you take the Earth, you size it down to the soccer ball, that's the ratio of sizes between your single quantum dot and the
Yeah.
ball. So they're pretty tiny. But you see, at those scales, it's difficult to explain how tiny something is. You sort of like, I think the key message is they're really tiny.
You're right. Okay.
Think of something tiny
Yeah.
more, right? That's good enough.
Okay.
So like their size is like around 10 nanometers. And then so why people care about these quantum dots is, and really you should be interviewing the guy who invented them, who's
Right.
sitting 2 buildings away from here, not me, but
Oh wait, the guy who invented them is here.
of course he got the Nobel Prize in chemistry
Okay,
2 years
okay.
ago. So and he's from MIT.
Yeah.
So the reason why people care about these things is because sometimes, and this happens for these materials, specifically semiconductors, when you make them really, really small, their properties change.
Okay.
And this is not intuitive. Let's take a simple example
Uh-huh.
and explain why it's not intuitive. Like if you take your
Wait, what do you mean by intuitive?
why it's not intuitive that these materials change property when you make them small.
Okay.
This, like, trying to draw a parallel here, okay?
Yeah.
So if you take a block of kitchen salt, like sodium chloride, you break it in two,
Uh-huh.
you taste it, it's salty.
Right.
You break it in two,
Yeah.
you taste it, it's salty. You go on breaking it in two until you get the smallest chunk of sodium chloride you can get,
Right.
and it's gonna taste salty.
Yeah.
Right, and that's more or less what you expect for a lot of materials. Like you
Right.
take glass, you break it in parts, and it's transparent and like resistant to acids. So, and you keep breaking it in parts, and it will behave the same. And there are some materials, among them quantum dots, which at some point they stop behaving always the same. They start doing other things. Two classes of materials that do this kind of stuff are metals. Metals, they do behave different. One famous example that is the one where actually the field was started in the 1700s, is a lot of time ago, actually, is gold.
Okay.
Like if you take gold, it's yellow.
Yeah.
You break it down, it's yellow. You break it down, it's yellow. At some point you get at the nanoscale, you keep breaking it down, it becomes purple.
Really?
Yeah, it becomes purple, red, all hues between blue and red.
Nice.
And that depends on the size of particles.
Okay.
Quantum dots do something similar. So you take the semiconductor that is like, I don't know, a piece of matter, like can be orange, can be gray, it doesn't matter, depends on the material, right? You break it into chunks, and at some point things start happening. Two important things. First, they become luminescent. So they become fluorescent.
Yeah.
Like if you
They
bring
glow.
them to, they glow. No, they don't glow alone.
Oh, okay.
Like you need to put them under black light.
Okay.
So if you put them under black light, they start becoming glowy.
Yeah.
And second thing is that the color of their glow depends on the size.
Right.
And if you think of it, that's very counterintuitive, because more or less in our daily life, you can tell a material apart from another by looking at the color, right?
Uh-huh.
Like you see, I don't know, if you like gemstones, a diamond is transparent, and like a ruby is red, emerald is green, gold is yellow. You can categorize materials based on the color,
Yeah.
and it's a simple way that we distinguish them. With quantum dots, that's not true. Like their color can change depending on the size, but the material itself stays the same.
Yeah.
Okay. So why is that so? Well, that's complicated.
Wait, so okay. Now we're on to when you break semiconductor. What do you call them? Like compounds?
It's compound, yeah.
Like you break them down into like a size that's small.
Mm-hmm.
It does one is
It starts glowing.
Yes, it starts glowing. So they glow with black light, and the color changes.
Yes.
That's the two things right now.
Yes.
Okay.
So the reason why we as scientists care about these materials is that light is a form of energy, right? And that's pretty important, especially nowadays, because energy means that you can do things. Energy in its essence, in its very fundamental essence, is the ability to do something. The ability is I think the definition is the ability of a system to perform a work, a job, right? So if you have energy, or you can control energy, then you can control what you do with that energy, and you can accomplish a task. And if you think of it, you are using photo-emissive materials in your daily life. Right now, like for this interview, if you're going to turn it into a video, someone will see it, and that someone will see it because their smartphone or laptop or anything has a screen which emits light.
Yes.
So the ability of us as technologists, as scientists, to control the emission, the production of light, means that we can do technology with them, right? In fact, the basic, like the main application of these nanomaterials is for LEDs, for screens, for illumination.
Oh, okay.
So that's the most basic use. Another interesting point is if a material is really good at emitting light, it's also very good at absorbing light, which means that the same material can become a very effective sensor for a smartphone camera or for a solar cell. So the fact that they interact with light so efficiently means that you can do engineering with them.
Okay.
So I hope I convinced you that there is a reason why we do this shiny thing. It's not just for fun.
But so is like when you're talking about quantum dots now, right? And they glow. The light part is the main part, but does the light convert to other forms of energy that you would use, or is the use mainly around like light emitting things right now? For example, screens.
You can choose. So there are actually a lot of possible applications for these materials. They all revolve around light somehow because these materials are really good at interacting with it.
Yeah.
One I mentioned already, so you can emit light.
Yeah.
That will make them useful in screens, but not only. For example, one application that is being explored is in nanomedicine, where you need to, for example, look at the tissue or like at a sample under a microscope, and you need to highlight something. One possible application is to attach these quantum dots to the object that you want to see, and then under the microscope this biological structure will glow and you are able to see it.
What?
So that is one possible application.
Sorry, Stefano, intermission.
Yes.
So I am helping. I just became a test subject for my friend. I'm in an experiment right now, and I have
Right
like,
now?
This,
Go ahead.
This watch is asking me how I feel every hour, and it just like touch this. It won't stop beeping unless I answer 36 questions.
Just go ahead.
So I'm
Just
gonna have
the
to
question.
answer this real quick. In the meantime, what's the rest of your week looking like?
Same as this one, I think.
Yeah.
Nothing much. I mean, working in the lab and doing things.
Is it a busy life being like postdoc?
Yeah.
I feel like everyone here is busy. Like this week I have spring break, and it's like, wow, I've not had a day in a while to just.
It's it's a tough life. I mean, it's fun. Otherwise, you wouldn't do it.
Yeah.
But there is so much to do.
Yeah.
The only thing that like makes it worth it is that it's fun. Because if it wasn't fun, no one would do this life, honestly.
Well, what makes it fun for you? Yeah.
I get to do something that no one else can. I mean, so I started as a scientist and since then I am rather sure that I have made at least two or three different materials that no one else in the world has done or knows they have done, which is also a problem because sometimes you just do it accidentally. But I'm sure about that, and that's cool. I mean, that is my material.
Wait. So okay.
Is it useful? No, it was completely useless material. But
really,
of course, but you cannot know until you do it.
Wait. Okay, we're done with quantum dots for a bit now. Like, what? You invented a material. You invented a new material.
Yeah, but I think everyone in that building does it routinely every day.
Really?
Yes, that's pretty much our job.
What?
What do you think material scientists do?
Well, it's true. Okay, but tell me, because I mean, I never thought about that actually.
Someone has to come up with ideas to make materials, right? So.
But what material did you make?
So the two I made were.
That's such a cool thing to say.
It's
like, I made a material.
it's still in the family of quantum dots, but mine weren't shiny. That is the disappointing part.
Okay.
So basically, they had no interesting properties. Some lead sulfide chloride nanocrystal salts.
That sounds like a very cool name. I love it.
I don't know.
Just put a bunch of like nanocrystal salts.
They are all nanocrystals. They are all salts. A lot of them contain lead. So actually, it's not your. Nowadays the coolest material that everyone is working on with it's cesium lead bromide nanocrystals, and it's a salt.
Salt. Nano lead salt crystals.
It's nothing really special. I mean, people who do my job, we do invent materials every day. We are material chemists, so. You have an idea of something that might or might not work, and you like mix things, do your reactions, and then at the end you check if it worked or not. Sometimes, actually, I think the coolest results come out accidentally. So like you're doing something and something else comes out, and then that's where you need your intuition to like realize that, that's cool, that's different. Like that's not what I expected, which means something is going on, and that is probably science. or like science worth doing.
All right.
That's fun. That's a fun part.
But so like when you say you invent a new material, right?
Mhm.
Like what about this material is new? Is it just a combination of it and it doesn't actually have like a new outcome?
It depends.
Okay.
It depends. So, for example, in my case, it was a new compound.
Yeah.
So it was a combination of elements like that has never been done before.
Okay.
It was a combination of elements in that specific ratio that has never been done before, and that formed a compound. For a chemist, like an organic chemist, could be a new molecule. For a polymer chemist, might be a new blend of monomers. It depends. It really depends. Our life is surrounded by materials, or by things that you can think of as a material or call a material.
Yeah.
Just look at your clothes. That will be like part of it is natural, right? It's cotton, linen, but then you have like polymeric fibers. Then you need to have the dyes to make them colorful. The buttons will be probably some kind of plastic. Those are materials, and they have properties. They are like not random. They are highly specialized properties. People choose those, like engineers will choose those materials because they have those set of properties. The ones that make your device work properly, or your piece of equipment work fine. That's the job of material science.
And it's a crazy job.
That's
like
fun. It's fun.
But so like okay, now back to the quantum dot stuff, right?
So a short recap. I think it's okay. Quantum dots, very small particles that are like very small crystals, 10 nanometers big, of semiconductors. Their main ability is to control, like absorb or emit light in a very controlled fashion. That's a recap, right?
Okay.
Imagine these tiny dots which like takes and gives light. So what's your question?
What are you trying to do with quantum dots now?
Me specifically?
Yeah.
Oh, that's gonna be complicated.
Like let's go.
Okay, so I was saying that the reason why people like me are interested in quantum dots is because they allow you to control the way you absorb or emit light. And light can have a lot of properties, right? One obvious property of light is the color that we already discussed about. The reason why we as a community think that quantum dots might be interesting is that there are hints or theories that suggest that quantum dots are able to emit quantum light. That is a type of light with specific properties, like it's really complicated to explain. But basically, it's a highly controlled and highly controllable light, which is so well organized in a way that you can use it to, for example, perform computations. And that is what would enter in a photonic-based quantum computer, for example. So I'm not going to do that. That's the point. I'm not going to do that because you need to realize the pipeline of science is very complex. It's very structured. And everyone is very specialized. Like there is a person who develops the theory, the person who makes the material, the person who optimizes the material, the person who takes it and puts it into a device, the person who makes the device work, so on and so forth. So my job will never be the one of doing a quantum computer. But my job is to make materials that have the properties that might become useful if someone wants to do a quantum computer. So that is the general direction, like to produce these quantum dots as quantum light sources. That's the direction.
Right.
That is pretty much.
But
you will need to find another friend to explain you why they work, because I have no idea.
But you are the foundation of because
we are the people who cook.
Yeah. No,
Yes.
you are the people who grow
The material.
the carrot.
Yes.
For the cook.
Exactly. Sort of. Yes.
That is great.
We invent the carrot.
Right.
Right. We invent the carrot. Yes.
That is so great that I got to speak to you first for this.
So now you can go to your friend who does quantum light.
Yeah, because I've been, I kind of came from like learning about quantum computing, and like
I have the impression that they don't even know.
No.
To be
like
honest.
someone described me as like, oh, we're inventing like a new state of material. I'm like, what dimension are you in?
No, okay, that's a problem with physicists. They like to make things sound more complicated than they are.
Right, and then the first time you said like, is like I asked you, you know, is it? It's a tangible material, like is it?
Mine, yes, it's a
Yeah,
tangible
yeah,
material.
and that
you can
makes-
touch it, then you will be intoxicated by heavy metals. So I wouldn't recommend. But
Really?
yes, it's full of lead, so
Oh,
it's not a great idea to touch it.
Okay, but so you produce quantum dots.
Yes, I make them.
How do you make quantum dots?
It's rather simple, surprisingly simple.
Okay.
So, in a typical process, what
In
you
a typical
do.
day in
Typical,
Stefano's
a
life.
typical day. So basically, let's say you want to make the specific material that I usually do. That is
Yeah.
like this cesium lead bromide.
Yeah.
So cesium lead bromide. What you do is that you take, your bottle of lead bromide. That is a salt. You buy it on the internet. You take some of this salt and you dissolve it to make a solution. You heat it up to a certain temperature. Then you need to add something that we as chemists, because we are fancy, we call them surfactants.
Okay.
The reality is that it's soap. I mean, that's just the fancy way to call a soap. It's a
Yeah,
surfactant. So you add some soap, and then you stir it so that the soap dissolves the lead bromide.
If you call it soap, they won't give you like a PhD anymore.
No, but that's what it is. It's soap. The surfactant we use is oleic acid, which is literally exactly
Right.
the organic part of that soap. So when I'm
Right.
telling you I'm using soap, I'm
Yeah,
not joking. And then you dissolve the lead bromide in this solution using the soap, because
Yeah.
that's its task. And then using a syringe, you inject another solution that contains cesium, and
Cesium.
which is another element. And they just the lead, the bromide, and the cesium suddenly are inside all together stirring. They find each other, they really like each other, and they crystallize. They create crystals.
Mm-hmm.
The role of the soap is to stop this growth at some point.
Okay.
So as these crystals try to grow bigger, the soap goes all around it and stops it. So
Right.
it keeps it small.
Okay.
Because one thing that, it's funny if you think of it, but the problem is not to make crystals, it's to keep them small. Because crystals really like to grow big, as we are used to see them, like big chunks in a gemstone or something. The challenge is to keep them small, and that's what soap does. Like it covers the surface and keeps them small. So it's really cooking, you take your
I
glass
see.
beaker, you heat it up, stir it, inject, wait,
Okay.
check the color.
So
It's cooking. Just don't drink it. Don't drink it.
and don't touch it
Don't. No,
either.
No.
What would happen if you did?
You would get intoxicated by lead.
Like you would throw up, kind of.
You would die.
You would. So
You would die, of course.
wait. So how much quantum dots would I have to touch for it to kill me?
I have no idea, and I don't want to find out.
Has anyone ever died from touching quantum dots?
No, but by touching, it's absolutely not advisable. Everyone at home, please don't do it. But in general, touching is not as bad because the skin is actually quite a good barrier.
Okay.
So you really need to swim inside them.
Okay.
But no, it would be much more dangerous if you drink them.
Okay. If
And
you
also-
have quantum dots, do not touch them. Do not drink them.
Also, okay, that's worth mentioning. That's very important because otherwise Sony will go after you with lawyers.
Okay.
Not all quantum dots are toxic.
Um,
The one that I do research on are toxic,
Okay.
but the ones that Sony uses for their quantum dot TVs, they are not toxic. They
I
are made
love
of
it.
other elements. They are totally fine. Don't freak out. Keep using your TV.
Disclaimer.
Yeah, no, that's important because otherwise, you
Yeah,
can
yeah.
make distrust. No. Of
Wait.
course, the quantum dots that we do are for scientific research purposes, and so we can handle them being toxic. But that's the job of a chemist. When they move towards the production,
Yeah.
like industrial,
Yeah.
uses, then no toxic material is allowed anymore. And we actually, one big challenge of our field is to find replacements that work as well, but they do not contain toxic
Right.
elements, and that's a big ongoing challenge. And companies who manufacture and produce quantum dots based objects, of course, they don't use the toxic ones.
But so currently in our TVs right now, are there quantum dots inside?
The QLED TVs
Yeah.
contain quantum dots. Yes,
So common TVs everywhere.
high end.
High-end TVs, okay.
QLEDs are not cheap.
Oh, but it's like you can go to the mall and buy these.
I have one at home.
What? I didn't know. Okay, wow, that's crazy.
Okay, so I think here there is an opportunity to chat a bit about something that's like Let's Blow Your Mind part 70,000
Okay.
or something. So people think that nanotechnology is highly innovative, that is, groundbreaking, that is, just exists in the lab, it's sci-fi. And
Yeah.
Quantum dots are, in a way, they are new, like I think they were invented in the 1980s. But nanotechnology by itself, it's first rather common in our everyday life, and it's pretty old.
Okay.
So the example that I was telling you about gold nanoparticles that become red, etc. Romans in the 1st century after Christ were doing it routinely. There are proofs of glass that is colored by gold nanoparticles back to Assyrians 2000 years before Christ.
But did they intentionally do it?
No, of course not. They didn't know. They didn't know, but they found out accidentally that if you mix, if you're making your glass and you put some gold salts inside and you heat it up, the glass comes out red, and it's very nice red.
Right.
Well, just keep doing it.
Yeah,
That doesn't matter. The first who realized that he got very small particles was wait, what's the name? Now the name doesn't come to my mind. It will come to my mind later, I'm sure. But that guy was the first who realized, understood, okay, I'm doing really small particles of gold, and that's why they're red.
Gordon Ramsay.
No, it's not him. It's not him. Oh my God! No, I need to find it. No. It's. I cannot go on as a chemist and don't remember this.
Louis Armstrong.
No. Come on. History. Faraday, of course, Faraday.
Of course, yeah.
Michael Faraday. So he was the first one who understood that red color was coming from very small particles of gold. But again, nanotechnology of this kind is pretty much everywhere. And you have used it, I'm 99% sure. You have used it in first person, like yourself, in the last 5 years. Can you guess where? I'm 90% sure you have used exactly those particles.
In our phone?
No. A hint, last 5 years, it was very specific. What happened 5 years ago? COVID.
In the vaccine?
No.
Oh.
No. Vaccine is proteins. The COVID tests. The red line that comes in COVID tests is gold nanoparticles.
Oh. Like... Okay.
I promise.
I'm trying to guess what what.
It's functionalized gold nanoparticles. So it's gold nanoparticles, and on the surface they have attached these small molecules that recognize the virus. And if the virus is there, they just attach, and then you see
color.
the line. No. The color is always there, but they become sticky. So basically, they react with the virus to become sticky, and that's why you see the line forming. If the virus is not there, they don't become sticky and they get washed away.
That's wild.
That's current nanotechnology.
So it's nanotechnology that is able to bind with a specific kind of virus.
Yes, and it's pretty straightforward. I mean, people have been doing it for years now. It's not nothing new actually.
Right, but I mean, see, most of the world, it's insane.
Because most of the world is too busy watching the football league. If they cared about something more exciting, they would know. But,
well, it's that's you talking about your whole country.
Yeah. But no. I mean, it's really everywhere.
Yeah. No, I interviewed someone recently on nanoparticles to bind with it's like an antidote for bees.
Okay.
And
it would work similar. It would work similar. Yes.
That was insane.
It was similar. And other examples of nanotechnology that you have around us, well, the processors and CPUs inside the modern electronics, they are nanostructured. Like the size of some of the features that make them work is comparable to quantum dots, more or less. That's like when when you buy a new laptop and there is like Intel Core or these kind of things, and there is like 10 nanometers or 2 nanometers or 5 nanometers technology that refers to the size of some components inside the processor, and it's about that size. So like it's very, very current nanotechnology. Other examples of particles are, the quantum dots in the TVs, I already told you, but some metal nanoparticles are often used as additive in fuels for reasons like they make the engines run better. They are used in catalysis to accelerate chemical reactions. They are added in paintings to make them like non-sticky or like help keep them clean. They are used in cultural arts restoration to like restore paintings or stuff like that. You can really do a lot of stuff because they are so simple and cheap to make. Another example of, actually there are some natural nanoparticles that are really cool, and they have properties that stem directly from the fact that they are nanoparticles. I really like them. I just cannot afford them. But do you like opals? The stone, the gemstone.
Yeah, I mean, I don't have an opinion of it.
But do you like
they're pretty, yeah.
They're pretty, right?
Yeah,
They're pretty.
yeah.
Well, those are nanoparticle solids. So if you go, you cut them one, and you check it under an electron microscope, you find out that they are actually aggregated nanoparticles of glass.
Okay.
And they are completely natural. They just form spontaneously. So.
Okay, so going again, just back to the quantum dots, and you were talking about you making them.
Yeah.
And you just mix a few ingredients together, and then you get quantum dots.
Yeah.
If I had those ingredients at home, could I technically make it?
No, because you're not a trained chemist, and it will be dangerous for you.
Okay. That's why you have a job. That's why you did a PhD.
Sort of. No, I mean technically yes. You have a recipe, you make it.
Yeah,
I mean I did it during my undergrad studies, so you definitely can. As everything, you learn how to make them.
Yeah.
And, But yeah, no, definitely you don't do them at home for safety reasons.
Oh right, because you can get killed. Okay, but so like what on the day-to-day now that you're at MIT, what are you doing? Are you just working to make these dots each day, or like?
I already developed the synthesis for them, so I already know how to make them. Now it's more about studying their properties and their structure.
Oh, okay.
Actually, I'm mostly studying their structure.
Okay.
Because again, we scientists, we are super specialized, right? So on a single topic, several hundreds of us will study all different aspects of one material. So for me now, it's more about studying how they are made, what is their structure, where the atoms go, what they do. That is mostly my day-to-day basic. But it's really, in a way, mine is blue sky research, so it's very disconnected from everyday reality. The applications, there are no immediate applications that come out of my experiments, and that's all right. I mean, that's okay. That's the reason why there is public research, right? Because you need someone to do all this kind of heavy lifting of blue sky research before you find something that can go into an industry, and then the industry will do.
Blue sky research meaning you just kind of find whatever.
It's a curiosity-driven research with no immediate economical outcome.
Right, and then hopefully you come across something and you're like, wait, maybe we can use this for something.
Yes, but usually, what will happen is that you sort of maybe patent it if you understand, but then it wouldn't be you who make it.
Okay.
You turn it into something useful. It will be like a company or someone. Because that's not our job. Our job is to try and think in the most free way possible, and just create, invent, find. And then when you finally establish something that is it works, it's useful, it's cool, you move to something else.
Right.
Because that's not our job.
Right.
Or it depends. I mean, maybe you are more like an industrial chemist, and then that kind of person would replace me in the project, right? But this is not my job.
Okay. Well, just to wrap this up, like what do you hope to do with this? Like, is there a specific thing you're just like day by day?
the hope is that if I manage to finish the project down to the end, I will manage to mount these quantum dots inside the chip to be able to convert light. So it would be a proof of concept, like to demonstrate that you can do it with them. That is the final goal. And I mean, you can think of it like what could it be useful for? For example, I don't know. Imagine the flash of your smartphone is a small chip that emits light, right?
Yeah.
Something like that. So to prove that you can mount them in a
Right.
chip and emit some light, that would be a possible ending.
Wow. That's crazy.
Let's see if it works.
Wow. You've blown my mind. Yeah, I don't know what else to say. Anyway, that was super cool. Thank you.